I'd like to thank the organizers and Claire for inviting me. So this talk is going to be about joint work that I did with Colleen Robles that is based on earlier joint work with Greg Perlstein and Philip Griffiths and Mark Green. And it builds on Colleen's talk to a certain extent. And it's also strongly tied to the other talks we heard today and Christian's talk and other talks, and its emphasis on the Hodge theoretic boundary, which I won't get to immediately. But so there are many ways to motivate this material, but I'm going to sort of choose the arrows to all run this way for this, the motivation for this talk. And so the idea will be to use representation theory to say what is possible, to classify what is possible for variations of Hodge structure with given symmetries or Hodge tensors, and use that in turn to decide what is geometrically possible or expected in terms of moduli, degenerations, and so forth. So for instance, if I can classify the possible Mumford-Tate groups, which was completely done by Stefan Patrikis, based on work I did with Griffiths and Green and earlier work by Simpson, and of course earlier work by Deline. If you can classify those, then you classify all the possible Hodge tensors, and of course the Hodge tensors are supposed to be algebraic cycles, the Hodge tensors of all types PP. And so it predicts by the Hodge conjecture the existence of certain cycles. So if we think in terms of flag varieties, which are the compact duals for Mumford-Tate domains that Colleen introduced, and I look at Schubert varieties inside those, if I know the maximal dimension of a Schubert variety, for example, then I can figure out what's the maximal dimension of variation of Hodge structure in terms of the image of the period mapping, and then I can ask about geometric realizations of this. If I can classify the nilpotent cones of commuting nilpotent elements in the Lie algebra, then this leads to classification of boundary components and hence to potentially degenerations of algebraic varieties, which would have applications to Torelli. Then if you study the geometry of the flag variety D-check, the compact dual, for instance, the second fundamental form, then this might give you information about differential invariance of variations of Hodge structure, and you can ask about geometric realizations of those. I will talk about this. And finally, you can go the other way a little bit. I mean, there are other ways to go the other way, but this is what I'm going to do as an example. You use the boundary components to define certain things called enhanced SL2 orbits, and they give smooth representatives of classes in the cohomology of D-check. So that's just one thing you can do going back the other way. So let me start by reviewing what a Mumford-Tate domain is and establishing some notation. So I have a non-degenerate, for this talk, symmetric bilinear form on vector space over Q. And I'm going to think in terms of weight zero polarized Hodge structures only for a bit. And these are going to be homomorphisms from the unit circle and the complex plane, thought of as a real Lie group, to the automorphisms of VR preserving Q. And that's sort of the first Hodge-Riemann bilinear relation. If you think of this phi as a polarized Hodge structure, and the second Hodge-Riemann bilinear relation would then be this positivity condition. And again, the way to think of these as Hodge structures is to look at their eigenspaces. These are the HPQs. Since they're defined over R, these are conjugate. Now I define G, my Mumford-Tate group, which is usually called the Hodge or special Mumford-Tate group, but for me is Mumford-Tate group, to be the Q-algebraic closure of phi of S1 inside of VQ. And equivalently, this is a theorem of Deline, G is the subgroup fixing Hodge tensors pointwise, and that is proved using Chevallier's theorem. Then we define something called the Mumford-Tate domain, which sits inside a compact dual and generalizes period domains. And this is just the orbit of phi under G of R. I'm going to ignore any connectivity questions. And note also that the compact dual and the Mumford-Tate domain have nice homogeneous descriptions. So the idea is to think of them as parametrizing a connected component of all Hodge structures on V polarized by Q with the same Hodge numbers as phi, and whose Hodge tensors include all the Hodge tensors of phi. And I'm going to talk about Hodge representations. When I mean that, I just mean VQ phis in this setting. Okay, so if you wanted to, how would you arrange for the Mumford-Tate group to be G2 or F4 or something like that? One way is to take, and this is maybe lazy, but you can take V to be the Lie algebra itself. And then you need the crucial assumption that G of R contains a compact maximal torus. It's easy to see this is a necessary condition to be a Mumford-Tate group, since if you take a torus centralizing phi, then it's going to be contained in the isotropy group of phi, and the isotropy group of phi by the polarization condition is compact. So now I let GR equals K plus K perp be a Cartan decomposition where the compact part contains this torus and an involution theta, which is going to be minus the identity on K perp and plus the identity on K. And I take the roots, delta, decompose them into compact and non-compact roots for K and K perp, and then I take the root lattice inside the usual lattice in X star of TC. And of course, these are the same because I'm taking G to be an adjoint group. Now, the fact that theta, the Cartan involution, is a Lie algebra homomorphism means that there is a homomorphism, just define it on the simple roots, from the root lattice to Z sending delta C to 2Z and delta N to odd integers. And since G is adjoint, R is lambda, and this homomorphism is actually lifts to a grading element in the Cartan subalgebra. And now we set phi of Z, our Hodge structure, to be just the exponentiation of this E. And then you get immediately, it's a simple computation from what I said before about theta, that this is true. And as a result of that, you get that G, add theta, add phi, and minus B, where B is the killing form, is a polarized Hodge structure of weight 0. And again, that's just because what I said about theta and its positivity on K and K perp means that this is going to have the right positivity conditions for this to be a polarized Hodge structure. Okay. Now, the Hodge decomposition can be read off very neatly. It takes this form, where Gj is Gj minus j, and you can write this as a sum of root spaces because I'm taking roots with respect to t. And I claim that the Mumford-Tate group of ad composed with phi is G. Remember, I chose phi sufficiently general. So I can take M in G to be equivalently the smallest Q-algebraic group, such that ad composed with this conjugate of phi factors through M of R for all conjugates by elements of G of R. The Mumford-Tate group of the family of polarized Hodge structures given there, and the Mumford-Tate group of any particular conjugate by an element of a meager set, complement of a meager set, complement of a countable union of proper analytic subvarieties of GR. And so the point is, because I chose phi sufficiently generic, this is the Mumford-Tate group of phi, and on the other hand, this is normal inside G. And so since G was assumed simple, see, I'm cheating on many levels, but this is one way to do this. So now let me remark that the dimension of D check can be read off from the sum of the HJs for J positive. Remember, HJs were just the dimensions of those GJs, which involves just counting roots. And the rank of the horizontal distribution is just H minus 1. Maybe it's better to think of the dimension of D check as the sum of the H negative things. So here's an example. So use this laser pointer. These root spaces, so this is a projection from the roots for G2. I've also drawn a little thing for the Cartan, down to the integer line. And you can see how many roots lie above each integer down here. And so, for example, the Hodge numbers are going to be 1, 4, 4, 4, 1. This is a weight 0 Hodge structure. You can also look at the Hodge numbers induced on this Hodge representation, the unique 7-dimensional irreducible representation of G2, and you get a level 2 Hodge structure of type 2, 3, 2. Just notice that the compact roots go to even integers and the non-compact ones go to odd integers here. Also notice that the tangent space corresponds to these roots, and so has dimension 5. So D check has dimension 5. The horizontal distribution has rank 4 because you count up these roots here. Okay? So it's very easy to draw these pictures when things are rank 2, but you need a computer when things are in higher rank, or you need a general argument better. So to generalize things a bit from that G2 example, what is a fundamental adjoint variety? So upon fixing a set of positive roots or set of simple roots, I have dually simple roots and simple grading elements on the one hand, and fundamental weights and simple co-roots on the other hand. And now I take any dominant weight, and I'm going to assume that the irreducible representation with that as its highest weight is real for simplicity, and consider the associated parabolic subgroup. This Borel B that contains my Cartan, its the root vectors are just the root vectors corresponding to the positive roots. And then I'm going to define what the P is by this criterion here. The non-zero mu i's have to correspond to the negative root vectors which are not contained in delta of the parabolic. Okay? So those negative root vectors are not contained in the Lie algebra of the parabolic. And so this fixes the parabolic. And I define also an associated grading element here. And this is an integer. This m equals e of mu. And what it's going to tell us is how wide the Hodge decomposition on U is. Moreover, this is a sort of Calabi-Yau Hodge structure because U of m is one-dimensional when I set things up in this way. So it's just a way of getting a bunch of Calabi-Yau Hodge representations, if you will. And then the GC orbit of U mu, this line in PU, gives a homogeneous embedding of GC mod P into PU, which is minimal if the mu i's are all 0 or 1. Okay? So the adjoint case is where U is the Lie algebra itself. And root weight computations show that m is equal to 2. So the Hodge numbers are these. I don't know what the stars are. They vary. But the outer ones are 1. And it is level 4. Unless G is of type E8, there exists a level 2 faithful Hodge representation, like 2, 3, 2, but with bigger numbers in the G2 example. And unless G is of type C, Cn, Cartan type Cn, the adjoint variety D check is minimally embedded in the PG. And unless G is of type AN or CN, the adjoint representation is fundamental, and the corresponding D check are what I'm going to call the fundamental adjoint varieties. So why should I care about these? Well, the horizontal distribution in each of these cases is non-trivial, so you have a serious Griffiths transversality condition to handle, but it's sufficiently simple as to be nice. So it's a contact distribution. So sort of, I wouldn't exactly call them building blocks, but they are the simplest examples to handle. Okay, so let me recall the result of Colleen about Schubert variations of Hodge structure in classical subdomains to get to why we started this project and what the motivation was, or what first questions were. So I start with the Mumford-Tate domain. F dot is going to be a base point. F dot is the Hodge filtration corresponding to the Hodge structure phi. And then I take the corresponding Hodge decomposition, T delta, all that stuff as before. Okay, so P will be the parabolic fixing the Hodge flag. And in particular, the roots of P are just going to be the positive, they're going to be the roots which go to, under that projection that I showed you before for the phi, the things that go to 0, 1, 2, etc. Okay? The positively graded roots, the non-negatively graded roots. So now I put WP to be this morass, which you can see as simply the minimal length representatives of the quotient of W by the Weil group of G naught, the 0 graded part. And there's something that you can write down, delta W, the intersection of delta minus the negative roots with the Weil transforms of the positive roots under little w. And the reason you want to write these things down is D check has a decomposition into Schubert cells for W and WP, which looks like this. And the Schubert varieties that one wants to study are the Zariski closures of translates of these Weil translates of these Schubert cells. And their dimensions are given exactly by the length of W, which is the number of elements in delta W. The tangent space is given by NW, which is the direct sum of the root spaces for delta W. And XW, I will call it a Schubert variation of Hodge structure if it's horizontal. This is a C variation of Hodge structure, not an R variation. So it kind of, it's a little bit of abusive notation to call it a VHS, but I will anyway. This is a subvariety of D check. So it is, in fact, horizontal if and only if NW is contained in G minus 1, which then implies NW is abelian. I'm sorry? It could be entirely outside, but in fact, for the ones that I will look at, they won't be. I mean, in fact, I took my base point. The way I've defined them, this one will always be it will not be outside completely. Okay, so this is really a corollary of a beautiful theorem by Colleen, but the corollary says, what is written there, that the maximal dimension of an infinitesimal variation of Hodge structure, an abelian subalgebra of G minus 1, is the maximal dimension of a Schubert variation of Hodge structure, which is computable because it's just this thing here. And so here's an example of how to compute it for our running example G2. So the point is, here's my conjugate of WP, and I intersect that with the roots of that with the negative roots, and I have this NW, and that has two roots in it, so I have a two-dimensional Schubert variety. And it's a Schubert variation of Hodge structure because this only intersects stuff in G minus 1. If I try to go to a higher dimensional Schubert variety, that doesn't happen. And so the maximal integral manifold of the horizontal distribution, and hence the maximal dimension of the image of a period mapping, is 2. And you can ask whether this XW is a Mumford-Tate subdomain. And this was the first question that I asked Colleen when I saw this result. And the answer is no. So it would be a smooth Hermitian homogeneous G prime of R orbit for some subalgebra G prime in G, but that would have to contain the closure of NW plus its conjugate. And that has closure all of G. And so it is not a Mumford-Tate subdomain. So what is the relationship between Schubert variations of Hodge structure and horizontal Mumford-Tate subdomains? So for any subdiagram of the Dynkin diagram of G, there is a standard construction of Schubert varieties, which goes like this. You take the subalgebra generated by the root spaces in the sub-Dynkin diagram, corresponding to those simple roots, and you take x of d prime to be the orbit of f dot under that G prime. That's a smooth Schubert variety, and it's horizontal if and only if G prime is contained in there, in which case it's the compact dual of a homogeneously embedded HSD. And so a little result in our paper is that if x in D check is a Schubert variation of Hodge structure, then it's smooth if and only if it is a product of homogeneously embedded Hermitian symmetric subdomains. And what does this have to do with Mumford-Tate domains, and what does it have to do with a result it calls to mind, namely the theorem of Friedman and Laza, that if x is a smooth VHS in that sense, y is a non-empty connected component of its intersection with the actual domain with strongly quasi-projective image in D mod gamma, then y is a Hermitian symmetric Mumford-Tate subdomain. So this is a completely different result. So this is a corollary of our result, and this shows the contrast. So here, you're making a much stronger hypothesis on x and a much weaker hypothesis on y. There's no hypothesis on anything having to do with gamma. So this is a purely geometry of D check kind of result. The converse of the corollary, interestingly, is false, because there are plenty of non-Schubert horizontal Hermitian Mumford-Tate subdomains, and I'll show you how to construct some of them. Okay, so I want to go quickly through this because I want to make sure I get to the material on the boundary and have time to go through it more slowly. So the corollary suggests there might be lots of singular Schubert variations of Hodge structure because the G2 example was one where it was not a Mumford-Tate subdomain, so that means it's necessarily singular. So a systematic construction of Schubert varieties, and in particular of singular ones, is given by the incidence correspondences shown here, which are sometimes called Tietz correspondences. So you have two parabolics standard with respect to the same Borel, and we note that these operations, x and x inverse, preserve Schubert varieties. A point is a Schubert variety, so p mod p is our f dot on the right-hand side. And x of the point q mod q recovers the previous construction of Schubert varieties from sub-Dynkin diagrams. Okay? But it does more, because if p is maximal, then I of p the set of simple roots whose negative root spaces are not contained in P is a singleton. And so if I of Q contains the nodes adjacent to this singleton, then x of d prime is a P1 through F. And the reason why that's important, going back to this diagram, is now what I can do is I can sort of smear this P1 around by the action of the isotropy group of F dot. And that's what this construction does. This is a Schubert variety consisting of all P1s through F dot on D check in its minimal embedding. And if I look at the case where D check is a fundamental adjoint variety, then beautiful stuff starts happening. So if I take C naught to be the G naught of C, G naught is the isotropy group, subgroup of G, subgroup fixing phi. So if I look at the G naught of C orbit of the highest weight line in PG minus 1, then this is a homogeneous Legendrian variety. This is sort of, I learned this from J.M. Landsberg, but it's based on work, I guess, of Stefan Kebicus and Yi. And moreover, this x naught is a cone on this C of 0. So we get Schubert varieties which are highly singular, which are cones through our fixed Hodge structure that we chose at the outset. So what do these look like? Here's some data for these fundamental adjoint varieties. These are the groups for which D check is a homogeneous space, and these are the groups for which the subadjoint variety C naught is a homogeneous space, the variety of lines through a point. And this is what they look like, and I'll just direct your attention to, here's our G2 mod P2 that we've been playing with. The G0, the isotropy group over C, the semi-simplification is SL2, and if you look at the orbit of the highest weight line in PG minus 1, which is a P3, you get the third Veronese reembedding of P1, the twisted cubic. So that will come back now. So let's relate these to some variation of Hodge structure object. So if I take a variation of Hodge structure of a complex manifold with associated period map phi from S to D mod gamma, where D is some kind of Mumford-Tate domain, and I denote by curly D a holomorphic differential operator on some open subset in S of order n, then this thing is OU linear. And so it depends only on the symbol of the differential operator. So what am I doing here? I'm including the N0 stuff in the VHS into the VHS, applying the differential operator to holomorphic sections, and then projecting to the 0n part. And the reason why this works is because I took the differential operator to be exactly of order n. So this gives rise to something called the Griffiths-Yukawa coupling, which goes from sim n of the tangent space of S to Hom from Vn0 to V0n. And this factors through, via the period map, via the differential of period map, purely representation theoretic map, sim n g minus 1 to Hom Vn0 to V0n. And I'm going to take the nth symmetric power map here, and I'm going to define star as the composition this way. So this gives me a map from G minus 1 to that Hom thing. And the Griffiths-Yukawa kernel is, by definition, the subvariety of PG minus 1, which is the kernel of this, the directions in the kernel of that. So here's an example. If I take the 7-dimensional irreducible representation of G2, here is a basis of G minus 1, and here are dual bases of V20 and V02, so G minus 1 acts in this way. And this is a highest weight vector for G viewed as a representation of itself. Now, given some element of G minus 1, you compute the action of this element twice in this basis with respect to this basis on this end and this on the other end. You get this. And that defines the twisted cubic. So this gives a Hodge theoretic interpretation to the subadjoint variety in that particular case. But it generalizes somewhat. So it generalizes to E6, E7, F4 by this theorem, and to a couple other cases via just computation. But this result says that for D check, a fundamental adjoint variety and V a level 2 Hodge representation such that V20 is a faithful representation of the isotropy Lie algebra. We have that the Griffiths-Yukawa kernel is equal to the subadjoint variety, the variety of lines. So this, on the surface of it, if I just sketch it, it's 3 lines. So if I start with a direction in y, then by definition that just means that xi squared acting on u is 0 for every u in v2 0. So now fix an element in G2, which is one-dimensional, which is not 0. So add squared of xi acting on v is in G0. So that moved twice to the left from G2 to G0. Then if I let that act on u now, then the only way you can get something non-trivial is to move u from v20 to v11 to v02 and then back to v20. That's what that xi v thing says. And that's 0 because we know that xi squared of u is 0. And so because of the faithfulness of the action in the statement of the theorem, you get that add squared xi of v is 0. And so the second fundamental form, this requires a little work. Second fundamental form vanishes at xi, and xi is in the variety of lines. Okay? Second fundamental form for the minimal embedding. So when the conclusion of the theorem holds, y gives a Hodge theoretic meaning to c naught gives a homogeneous description of y, and this is what I like. Add squared xi of v produces explicit projective homogeneous equations for both of them at once. Okay. So now I want to talk about the Hodge theoretic boundary. I will stop blitzing. So let me start over with a Mumford-Tate subdomain of a compact dual, parameterizing weight 0 Hodge structures on V, as usual. V might be the Lie algebra, might not. Let gamma be a neat arithmetic subgroup of G of Q. And then I take a cone. This will be the closed cone. This will be the open cone, generated by M computing nilpotent elements in GQ. And I'm going to define boundary components in the following way. So I want all f dot in D check such that this should be a tau. E to the sum of tau I ni f dot is in D for the positive, strongly positive imaginary parts. And for every I, ni drops the Hodge filtration by no more than 1. And then that parameterizes limit mixed Hodge structures of the form f dot w of sigma dot. What is w of sigma dot? Okay, so we can define it uniquely in the following way. Take any n in the interior of sigma. Then I can uniquely determine w of sigma by requiring that n drops the weight filtration by 2, and n to the k gives isomorphisms between the grade weight k and grade weight minus k parts. And it's essentially the theorem of Catani and Kaplan and Schmidt and Deline that this does not depend on your choice of n in the interior of sigma once we have this sort of polarization condition going on here. So this is actually a very non-vacuous assumption. Okay. So now the actual things I want to call boundary components are the quotients, the left quotients of B tilde of sigma by e to the complex vector space generated by sigma. And this parameterizes not limit mixed Hodge structures, but limit mixed Hodge structures up to reparameterization by local change of local tangent vector or holomorphic coordinates. And so this parameterizes sigma nilpotent orbits. That's another way to think about it. And B bar of sigma is the thing that you are actually going to adjoin to D modulo gamma to get some kind of partial logarithmic compactification of D modulo gamma. So this basically, the statement here is simply that this extends the results of Kato and Usui on period domains D mod gamma to Mumford-Tate domains D mod gamma. And so you get a logarithmic manifold when you do this, and so there's some kind of topology on the disjoint union of this and D mod gamma. But I won't go into any more details about this. Could be useful for moduli, though. All right. I'm interested in the structure of B of sigma and B of sigma bar, just on their own. Let's write M sub sigma for the Lie group associated to the Lie algebra, given by the image of ni, of the sum of the ni, intersect all of the kernels of the ni. And let Z of sigma be the centralizer of sigma in G. The actual centralizer is what I want. And this is supposed to be basically a Levy decomposition into the grade weight 0 part and the weight minus 1 part. And this is a statement. I'm making a statement here saying that the weight minus 1 part is M sigma. So G sub sigma in Z naught of sigma is defined to be the Mumford-Tate group of the generic split associated graded of the limit mixed Hodge structure. Then you get the following fibration, B of sigma to D of sigma, by taking a limit mixed Hodge structure and doing this associated graded splitting. That's the interpretation of points here going to points here. And I also have a section of this coming from a choice of Q split F naught comma W of sigma. So using that section, I can write B of sigma as a semi-direct product of the semi-simplification of G sigma, the real points of that, semi-direct product, this is an almost direct product, M sigma of C, acting on F naught dot, and D sigma is just a Mumford-Tate domain in its own right. It's just action of a real group on a bunch of, basically on a Hodge structure, which is a direct sum of Hodge structures in various weights. So this is again in the nature of just pointing something out. There's something called the naive limit map. And I love to talk about the naive limit map because when I first learned Hodge theory as a graduate student here, one of the first things I read was this transcendental algebraic geometry volume, where you're sort of told as an aspiring student in Hodge theory, you should never do this. That's why I call it the naive limit map. You're supposed to twist by e to the tau n before you take the limit of a Hodge flag to compute the F lim. But here, we're just taking the limit without doing anything like that. So this is supposed to be the, I mean, if you have a variation of Hodge structure, I suppose I'm slightly messing up how I'm saying this, but it looks like I'm doing what I said I'm not doing, but trust me. I'm just taking the naive limit of a nilpotent orbit, and it's going to hit the boundary of the period domain, and that's where the limit is going to lie. If you take the limit mixed Hodge structure normally, then you sort of translate that somewhere, and then the limit lies outside the period domain, inside the period domain, on the boundary. It could lie anywhere. But this one will always be on the boundary of the period domain in D check. And this gives, the reason why you want to study this is this gives a relationship between sort of nilpotent GR orbits in the nilpotent cone and GR orbits in the boundary of D. And there are very strong sort of combinatorial relations between these things, which I have been studying recently with Greg and Colleen. Okay, so my paper with Colleen contains a general prescription for using a set of strongly orthogonal roots in G1 to explicitly construct Q-split base points sort of living on the boundary somewhere. And the motivation is to parameterize these GR orbits in del D in the image of naive limit maps. But I'm only going to discuss S equals 1, 1b, 1 beta, and I am not going to worry about any of this GR orbit stuff, at least not in general. So fix a base point O. O will be the same as F dot, but it's useful to have two names for the point. And let beta be in delta of G1, and let the associated SL2 be this one, where n is in G minus beta. And now I apply the Cayley transform. This was in Colleen's talk in a different form. And here's sort of the picture of what the Cayley transform does. I have a point in the interior of the domain, and C beta takes it to the boundary of the domain, so it does this, but it also does this stuff. So it takes a complex carton whose real points are compact to a complex carton whose real points are non-compact. Sort of toggles between different G of R conjugacy classes of cartons. Takes these root spaces to these root spaces. The alphas will still have the same name, and this grading element to this grading element. Okay, then F prime is in B tilde of n by construction, and G semi-simple of n has this explicit description in terms of roots alpha strongly orthogonal to beta. And E prime y give a Deligne bigrading GPQ, where the GP, that grading, is by prime E, and GP plus Q, the weight grading, is by Y. And the dimensions HPQ are the Hodge-Deligne numbers of the limit mixed Hodge structure associated to O prime on the boundary. That's an R-split limit mixed Hodge structure. And if you set things up the way we do in our paper, which involves a strong arithmetic assumption on D, then it's actually Q-split. So we can use this to construct non-Schubert Mumford-Tate subdomains in the following way. basically you have orbits taking place in the boundary, and then I'm going to orbit them into the period domain by an SL2 or a product of SL2s. So here there's just going to be one SL2, and this is what the picture looks like. So I have G semi-simple sub n cross this SL2 operating on the boundary point. And that gives a subvariety of D check. And with an arithmetic assumption on O, this is actually a Mumford-Tate domain, Y of n, the intersection with D. This arithmetic assumption only applies to this statement. X of n takes the form D check of n. This is the compact dual of the thing that B of n fibers over, cross P1. And inside that, Y of n looks like that. D of n cross the upper half plane. And you can say exactly when Y of n is a Hermitian symmetric domain. And you can say, for the most part, that X of n is never a Schubert variety. Schubert varieties, basically, there's something about having P1 factors that they don't like. OK, so now to come to the boundary of adjoint varieties. Yeah? That was the motivation. Yeah. With which components? Holomorphic arc components. Ah. So there is a thing that generalizes holomorphic arc components called B hat. And that's what happens if you take B of n and you take its image by the naive limit map. That gives you this B hat of n. And it's not exactly, it lives inside a holomorphic arc component. It isn't necessarily one itself. But there's a distribution that Colleen has in a recent paper that you can show B hat of n as an integral manifold of it and so forth. So, but the B hat of n is, in some sense, what the non-classical analog of Bailey-Borel boundary components should be. So you can probably make some kind of very singular log manifold compactification out of their quotients by gamma n. OK, so now I take a fundamental adjoint variety. And because it's, the grading element is very simple. It's just a single grading element, dual to a simple root, alpha I. And we have this proposition in our paper, which I like. There is a unique codimension 1 GR orbit in the boundary of D in D check. And this is very useful for figuring out which open GR orbits in D check kind of can be Mumford-Tate domains of the proper type. So this is based on work I did with Greg showing all codimension 1 GR orbits of in Mumford-Tate domain boundaries are polarizable in the sense of reachable Hodge theoretically by limits. But it doesn't use that explicitly. So if I may, I'll just go through a sketch of the proof. And the first ingredient is a general statement that if you look at the Hodge-Deligne numbers associated to a point in a boundary stratum, a GR orbit on the boundary of D, then the sum of the HPQs with P and Q positive is its real codimension in D check. So you also know from the paper with Perlstein that codimension 1 orbits are of the form G of R acting on the Cayley transform of O by some beta in delta of G1. So with that, we are halfway there. And acting by the Weil group of the isotropy subalgebra, we can assume that beta has negative killing form product with all of the simple roots except for the one corresponding to the grading element. And moreover, G prime beta, the root space corresponding to beta, is in the 1-1 position. Again, that's sort of by construction via this Cayley transform. And so that's contained in the first Hodge-graded piece, and that's contained in G11. So that implies, because of the Hodge grading that is, by 1, so being in here, that it contains one copy of alpha I. And because it's a positive root, we know it's composed, furthermore, of positive, non-negative multiples of the other simple roots. The weight of alpha I, moreover, is given by its action on the weight grading corresponding to this Cayley transform by beta. And then I just plug this formula in here, and I let everything here act on h beta, and I get this. And we use the fact that this is non-positive to see that this is greater than or equal to beta of h beta, which is equal to 2. And so that shows, because you know this is 1, because the Hodge grading of alpha I is 1, that Q of alpha I is at least 1. And so then you have two things of type 1, 1, or 1, 2, or 1, 3, you know, and that would mean that the codimension is greater than 1 unless beta is equal to alpha I. So this shows that the thing by which we did the Cayley transform, in the end, it has to be alpha I. There's no other codimension 1 boundary stratum. OK, so now I let O prime belong to this real codimension 1 orbit with associated mixed Hodge structure F prime W n. And bigrading GPQ, then we can say exactly what the bigrading looks like, always, for all of these cases. And it has a lot of symmetries. All of these numbers in this hexagon are A, and all the numbers on the outside are 1. Why is that? Again, it's very easy. The dimension of G2 is 1 because it's a fundamental adjoint variety, 0 for greater than 2, and the same thing with the weight filtration. So alpha I and alpha tilde, which are these roots here and here, they are non-short roots, and you know this, and you can prove this, and so the upshot is that there's some Weyl element sending this grading element to minus this grading element, the Hodge grading element to minus the weight grading element. And so that means that W acts on GPQ, sending it to G. So GPQ is GP intersect GP plus Q. And when I apply W to that, it sends this to there with a negative sign, and this to here with a negative sign, and so I get that. And that gives you the sort of hexagon of A's in the picture up there. So we observe this computationally, but it's better when you can write a proof. So note that W identifies the faithful representations of G naught on G1 and G naught on G minus 1, the weight and the Hodge. And that's sort of the key to what I think of as it's sort of the main result on boundary stuff in our paper. And it goes like this. So D check of n in PG1 is isomorphic to the subadjoint variety C naught, the variety of lines in PG minus 1. So you're identifying the compact dual of the base of this boundary component with this C naught. So that means that X of n, which was this enhanced SL2 orbit, is a cylinder on C naught. So we have a sub-Mumford-Tate domain of D check that looks like a cylinder on C naught, where we had a Schubert variety that was a cone on C naught. I'll get to that in a second. Then B bar of n over D of n mod gamma n is a family of intermediate Jacobians associated to a variation of Hodge structure with Hodge numbers 1AA1 over a Shimura variety. Let me go back to the picture. This thing here corresponds to the Lie algebra of the Shimura variety. This is the Hodge representation, the 1AA1. And finally, over D of n, these variations of Hodge structure recover exactly the Friedmann law as a list of maximal weight 3 variations of Hermitian variations of Hodge structure of Calabi-Yau type. So they're somewhere on the boundary there. You've got a family of intermediate Jacobians coming from those families, and I don't know, applications? Maybe we should be looking for Fourier coefficients in the cohomology of these families for automorphic cohomology classes on D mod gamma. That's a possibility. But I'm going to say something about the other two applications. First of all, the cohomology of D check. So H star of D check Z is generated by Schubert varieties. And I apparently can't spell. And the horizontal part, which is invariant characteristic cohomology, was shown to be generated by Colleen by Schubert variations of Hodge structure. And so the irresistible question is, do the subadjoint cylinder classes X of n, the enhanced SL2 orbits, yield smooth representatives of the subadjoint cone classes X sub W? So cone on a twisted cubic, cylinder on a twisted cubic, they're comparable. They're not exactly the same. And the answer in general is much messier than the one I'm going to show you here. So XW, remember, is what you get when you look at this line, the orbit by this sort of dotted thing in red on this flag gives a P1, and then you smear that P1 around by the action of G naught. That gives you XW. So it's an x of this by this Tietz correspondence. X of n, on the other hand, is the orbit by SL2 beta of that thing. And these commute. And so it's a straightforward product. And that's where the cylinder comes from. Now we just compare the cohomology classes of sigma and sigma of n. Since omega 1 is 2 omega 1 alpha 1, and you can see where these things are. Omega 1 and alpha 1 are in these two respective algebras. Sigma of n is 2 sigma, and so x of n is 2xw. So it doesn't smooth the class of xw. It smooths twice the class of xw. So this is a kind of non-classical case of some things that in the Hermitian symmetric case have received a lot of attention. So it was something we wanted to think about. But the answer is messier in general. So I would like to conclude with an example of geometric realization in the G2 case, which was, which has been the running example here. So it begs to be said whether there's any chance at all to give geometric realizations for these exceptional groups. So for G2, a geometric realization should take the form of a one-parameter family of surfaces xt with H2 transcendental Hodge numbers 2, 3, 2. Mumford-Tate group G2 and limit mixed Hodge structures of the following form. So I want to realize not just the maps into Mumford-Tate domains, but I want to realize degenerations geometrically that correspond to the boundary components, these codimension 1 minimal degenerations. So by Clemens-Schmidt, this is what you would get. That would be H2 transcendental, if you will, of the singular fiber, including into the H2 transcendental limit mixed Hodge structure. In fact, there is a beautiful little preprint by Nick Katz, which uses elliptic fibrations to construct a one-parameter family of surfaces, actually 3 one-parameter families of surfaces. And the Mumford-Tate group is determined using some serious arithmetic, a moment computation using elliptic convolution over finite fields. And here's a special case. You start with a pullback of the Legendre family of elliptic curves. This has singular fibers I4, I4, I2, I2. Then, for any t that avoids those 4 numbers, you base change, fix t for the moment. T is just a number for the moment. You pull back by this. So they're both going to the same P1z, so it makes sense to pull back. And so this, because, well, what's going to happen is if you look at the singular fibers of this E, 3 of them do not lie over a branch point of this, but one of them lies over a branch point of this, namely the one at infinity. So you get 7 singular fibers. And it has holomorphic 2 forms. It has 2-dimensional space of holomorphic 2 forms. Again, you can say exactly what they are. They're written down there. And the dimension of H2 transcendental of xt is 7. So here's the way you build the cycles. Here's the ET. I have an elliptic fibration over this ET. The local system is trivial if I make enough cuts between these points. And in particular, on this side of the picture, the local system is trivial. So I have a rank 2 local system over this, a rank 2 local system over this. This gives me 2 cycles. Okay? Call the ones over here, A1 and A2, over here, B1 and B2. And I get sort of, I can glue Lefschetz thimbles together to get 3 additional cycles over these paths gamma I, gamma 1, 2, and 3. So moreover, there's sort of a natural bifurcation of the cohomology. I mean, if you want to study the 7-dimensional representation, it's natural to split it up in this way. So now if I degenerate xt as t goes to t naught equals 2 over 3 root 3, one of the points I said we had to avoid. And now I'm letting t vary so that I have a family of elliptically fibered surfaces. The degeneration looks like this. You can set this up so that the total space is smooth in the neighborhood of this fiber. And when you normalize, you get a K3 surface of Picard rank 19. You can work this out explicitly. And this E, along which the K3 surface is folded up, is a Legendre curve, and the J invariant is non-integral. So why do we care about that? Because its cohomology is going to appear in the cohomology of the singular fiber. So this is the cohomology of the singular fiber, and it takes exactly the form I said I wanted to realize a boundary component geometrically. And moreover, we can determine the limiting period in b bar of n in the following way. So first of all, there's the boring part of determining the point in H mod gamma. You just observe that because if you look at the Mumford-Tate group and you look at the piece that controls the split limit mixed Hodge structure, it's an SL2. And you already know the Mumford-Tate group of this is SL2. So that forces the Mumford-Tate group of this to be not just SL2, but for this Hodge structure to be sim2 of this over Q. And so we get that H2 tur of Y is sim2 of H1 of E, so all we really care about is H1 of E, and that's a non-CM Hodge structure of some kind. I didn't explicitly write down the J invariant for this talk, but you get the idea. And then the point in the fiber is also easy to figure out. The intermediate Jacobian of the Friedman laws of variation is very simple. It's just J of sim3 of H1 of E in this case. And because this is associated to this degenerate K3Y and to the elliptic curve. But what you really a priori have to look at is the Jacobian of this thing here. Because you're classifying an extension class. Let me go back to the picture. You're classifying the extension of this by this. And so you need to actually look at what I've written here. But G2 tells you that the extension class is actually going to live inside this sub-Jacobian. So this is 4-dimensional. This is 2-dimensional. It's still non-algebraic. It's not an abelian variety. But you can say explicitly what it is. And the point in this fiber is given by these two integrals. So these are not closed integrals on the K3 surface, but they're closed integrals on the singular degenerate fiber. And this omega is just any holomorphic 2 form on the K3 surface. So this gives rise to a problem. Because the image of the period map into D mod gamma is contained in 2-dimensional integral manifolds because of that observation about contact structure I told you before, or by Colleen's result. You have a 4-dimensional, rank 4 contact distribution inside a 5-dimensional variety, so you're going to have 2-dimensional integral manifolds. Does xt belong to a 2-dimensional family? Do you actually have a 2-parameter family with 2-dimensional period map image? For F4, amusingly, you expect a 7-parameter family of surfaces into the quotient of the fundamental adjoint variety with H2 tur like that. And so the last comment I'll make is that to determine which deformations of xt preserve G2, which is what you actually have to do, it may be, you might have to go outside the elliptically fibered situation. It may be necessary to see the cubic Hodge tensor geometrically. And so what you can try to do by starting out on the boundary and deforming a cycle into the interior is to build a cycle in Chow 3 of the triple self-product of this surface, inducing sort of a cross product from H2 tur to cross H2 tur to H2 tur. And you can write down a cycle which does what you want on the boundary. The issue on the singular fiber. The issue is getting it to close up to be what's called a motivic cohomology class on the singular fiber and then deforming it in. And with that, I wish everyone a good buffet.